in the next few years. That is the direction in which the research, the education, the investment is going to be interpretable models. So these are the requirements of some good learning algorithms. Right. Coming to decision tree, the very first tree which will strike you for decision tree is that it can be very easily interpreted. Right? It has a inverted tree-like structure. So when I'm talking about decision tree, it's not like the regular tree that you see, but it's an inverted kind of tree that you'll see. And this inverted tree is very easily interpreted. The other one, it can take into both categorical as well as continuous variable, which means that it can be used for both classification as well as regression kind of problems. So our requirements of a good algorithm, two of the main points, it is already solving, right? C, it's also quite robust to missing values and outliers. See, by the way, if you have missing values or outliers, it's generally not a very good trick. Right? Let me make this very much upfront. Having missing values and outliers are not a good trait to solve any machine learning or data science problem. Obviously, if the values are missing, or again, if the values are spread wide apart, the whole algorithm will fall into some kind of a problem, right? How you're going to interpret from data if the data itself is missing? How you're going to interpret from the data if the data is talking of things which is from of a very different domain altogether, very far off, right? So again, that will always be a problem, but in some sense, decision tree, they are some bit robust to missing values and outliers. Some bit robust, I'm saying, not entirely, some bit robust, right? Okay, so these are the your motivation for learning the decision tree. If I talk about the learning outcomes that we are going to have, one is how and when to build a decision tree model, right? How to ensure that your decision tree is not overfitting the data. Right? Overfitting, we are, I think, going to talk about in details tomorrow. But again, we'll start off with the basics today. Right? What exactly is overfitting? How do you ensure that your models are not overfitted? Right? Also, if it's a tree, right? So as you know, a tree can be a very small, like a bonsai, or it can be a very huge one, like a banyan tree. When you are using decision tree, a tree for taking some decisions on your behalf, how big the tree should be? Will it be as small as a bonsai tree, or it will be like a very big banyan tree? What kind of a tree are you going to have? Right? The depth of the decision tree is what we'll talk about. Some common interview questions which might probably come in your way for a decision tree. That's also something which I'm going to discuss. Right? Okay. The first thing, the definition is that, as I said, that it just creates an inverted tree-like structure. And in the inverted tree-like structure, what contains are some kind of decisions at every branch, at every nodes. And based on this decisions which are there in the branches, the values which are there in the leaves, right? You can do some kind of a prediction for a particular stream of decision. It's almost like predicting that, okay, you see that this particular part of the tree, it looks like very green. So probably this is the part which will give you a good fruit. Right? This particular part of the tree, the leaves have already fallen off. Probably this is not something which is going to give you a fruit. Right? That's what you interpret of a real tree. In a decision tree also, you can also employ the same kind of analysis, right? Let's see how we can do this. So these are some of the important things, right? The predictor values are what you are going to find out. The terminal nodes or the leaf nodes, how to stop, where to stop. These are also some of the things that we are going to discuss. And at the end of the day, it is a very popular predictive analytics technique. We use a flow chart like structure to give you this in that like format. So this is an example of a decision, right? if you see on the left hand side, it's a normal tree that you have. If you see on the right hand side, that is where you are probably talking of a decision tree. The image I have taken from this particular website, right? Full acknowledgement to them. But let's map it to something in the reality world. Right? Okay, so someone is trying to change his or her job, right? And typically, this is in USD because I mean, that's where we get some kind of a common benchmark. See, in the US, typically salaries of less than 60,000 are not considered to be at par or good for engineers. So first is that whether you're going to accept a new job offer or not. Now think about it from your aspect. For people who are living in Mumbai, Bangalore, what is the first thing that you take into account? One is how much raise it is giving me. Two is for people who are living in Bangalore, how much commute is there, right? We'll have to commute for less time or more time, right? What are the amenities in the company? Growth opportunities. These are probably some of the things that you take into account up to the part of taking the decision. The first one is salary at least 50,000 USD, 50,000. If someone is giving you that, well and good, you probably go in and try to accept that offer. If no, you are not interested in the very first part, right? So you decline the offer. The next part is the commute more than an hour. Is it asking for commute of more than an hour? If yes, problem, right? Maybe not very worth to take this offer because again, whatever increment you have got will probably be ending up spending on the commute part. No, then probably the amenities part. See, offers free coffee is one of the amenities. I'm sure that you're not going to take a decision based on that. But yeah, here amenities are there. Yes, accept the offer. Amenities are not there. No, decline the offer. So my question to you is that why we started off with this salary at least 50,000? We have started off with this offer free coffees part, or maybe commute more than 1 hour part, isn't it? Why do you think that this salary at least 50,000 is the one on which we have started splitting the tree? Okay, so some answers are there. So Pinkesh is saying that primary reason more critical, more important. Good. Anything else? Anyone has a different point of view? Primary reason more critical, more important. Sure, I'm with you. I'm with you. See, at the end of the day, whenever we are trying to take a decision, our objective is to have the variables through which we are able to segregate the decisions in the least possible number of steps. Right? Think about a water purification plant. I'm sure that many of you or most of you probably is having this aqua kind of things in your home. If you have more money, you can probably put in an entire water purification plant in your home or outside your home. Right? And obviously, as you know, that this particular plant will look into all the different aspects in which the water could be purified. But then how come a very small machine is doing exactly that? The thing that is happening is that there are so many different variables to consider when probably you are purifying the water. Right? Maybe some 50 or 100 different variables which are used for purifying the water. All of them might not be equally important. Some of them are more important than the other. If there is some particular aspect or feature which can help you reduce the impurity of the water, let's say by 70%, I'll probably select that one, that particular feature, compared to the one which can only purify the water by 30%. Isn't it? Same analogy applies out here. Some of you are saying that first, we need to take into account those decisions which are more important. More important in the sense that most of the people will consider this particular decision to be paramount when taking a yes or a no decision, right? So that's why you see that the salary part, if the salary is not a good one, I'm not going to a particular company unless I have some other reasons to join. If they are offering me a lower salary, no, I'm not doing that. So that's the first point to take into consideration, right? So once you see that salary part, see in this particular part of the decision tree, I don't have any further decisions to take. Already I have declined the offer. Already I have declined the offer, right? There are no more considerations out here. You're not giving me salary, I'm declining. Now you have admitted to giving me a salary, good, right? I'm interested. Now comes the other variables. Fine, I'm interested in the offer, but let me look into the other variables. What about the commute time? Which particular office are you going to put me? Are you going to put me in the office which is probably closer to my home so that I can have a good work-life balance, or something which is very far off? If it's something which is very far off, though you are offering me a raise, an increase in salary, but maybe I'll stick with my current job, right? So commute more than an hour, yes, decline offer. No further decisions to be taken, right? You have already taken the decision. Commute time is fine, good, right? Seems I'm interested, but my last organization, it also had some perks apart from my salary and all the other things. Are you giving me those perks? Yes, good enough. I think I'm going to accept the offer. No, I'll decline the offer. So these particular steps which we are talking about, right? As you have rightly said, that these are more important. Why it's more important? Because you think, that is your perception, that it is more important. Now, when you have been given a large set of data where the underlying variables, you don't know that how important are those underlying variables. Let's say you have 10 different variables. You don't know how important are each of these variables with regard to each other. In this particular example, you all could associate yourself with this particular problem. But in problems where you don't know the distribution of the variables, you don't know how important is one variable vis-a-vis the other, that is where some kind of a logical process or mathematical process will come in, step in. And the logic which you have applied here, they will also do the same thing. They will find out the most important variables first and try to split the tree based on that, so that at the end of the day, you are able to take a decision. That's what they will do, right? Okay, so these are some of the terminologies that you have in decision tree. Right? One is the root node. So typically, if I'm drawing a tree like this, right? This is where the root is there. Now this root is paramount for the tree. Why? Because this root is where all the nutrients are there, right? Nutrients, water, everything that is there on the root, right? So once you put these things on the root, that is when the tree will start to grow and will try to give you the results or the fruits. In decision tree, same analogy. In the root node, the entire data, the entire population is there, right? So that is the first terminology that you should know. Next is the part which is called splitting, right? Splitting is when you are dividing the data on two or more different subnodes based on some particular condition, right? Decision node, the decision that you are taking when you are splitting this particular node, right? That's the decision node. Branch is a subsection of the entire tree. So the root node is there. So root node is basically the one, the other of the entire tree. So once the data starts flowing from the root node, it goes into some branch or the other, right? So subsection of the sum of part of the tree is the branch. Leaf nodes, very important. That is the part which further can't be split. Obviously, you know also that in a tree, so first you have this trunk, then you have this branches, and this branches leading to smaller branches, and finally this leaves. And you further can't split the leaves, right? And then also there's something called depth of the tree, right? So I was talking about having a bonsai vis-a-vis having a big banyan tree, how big the tree should be, right? In terms of a decision tree, it is basically the length of the longest path from the root node to the leaf node. longest path, and the stopping criteria, that at what time you should stop growing the tree further. Right? These are some of the things that we need to focus on when we are doing this piece, right? So this is how a decision tree looks like. The decision tree in terms of a machine learning part. All data is there. Root node, right? We are splitting the root node based on some particular condition, right? Some kind of a decisions are being taken, right? Based on which the root node is being split, right? And then these decisions are leading to further decisions till the point there are no more splitting possible. So these terminal nodes are the leaf nodes. No further splitting is possible. They are the leaf nodes. In some of the cases, some of the branch will quickly lead to leaf. Some branches will take some more time before which they can give you the leaf. All depends on the kind of data that you have given, right? Even in trees also, you'll find that if the soil is very fertile, sometimes they will quickly give you the fruit. If the soil is not that kind of fertile, maybe they will take a lot of time to give rise to those fruits, right? Almost the same kind of analogy lies out there. If you see this particular part, this is a branch or a subtree. See, this is a tree by its own. This particular part is a tree by its own. Right? So in the sub branch or the subtree, this one is probably the root. And from this root, this is the other parts which are coming out. Okay, so Vinay has a question that what depth of the tree represent? Does it have any sort of significance towards what should be an optimal depth of decision tree should contain? We'll come to that point later, Vinay, right? I think we have to cross some more milestones before we can answer this, right? So be with me, hang on with me. You'll get your answer. Okay. So these are some of the decision tree algorithms. So ID3 is the very first algorithm which was there. This ID3 algorithm could only be used for classification tree. It could only be used for this classification tree. Then came the next iteration, which is C4.5. That could be used for both classification and regression, right? Could be used for both categorical as well as continuous variable, right? And then you have the C4.5.0, which is basically an improvement of C4.5 in terms of the performance which is there. You also have the kite decision tree, which is the chi-square tree, and you have the cart tree, which is basically an improvement of the C4.5, C4.0, which is the classification and regression tree. Right? In this particular part, we are going to focus on these things. To be more specific, cart is the one on which we are going to put our focus on. This is what most of the algorithm implementations also follow. By the way, quick question to you: in your STS, in your statistics class, have you been told about chi-square? Have you covered that particular part, chi-square for categorical variables? Has that been covered? Yes, no. Chi-square analysis of variance, has that part been covered in your statistics part? Okay, so Stevens is saying that that has been covered. Fine. Only Z-score test has been covered. Sure. Again, it was there in optional content. Fair enough. So I'll just give you the basic motivation towards that. I'll not dwell deep into the mathematical parts of the kite tree, right? But again, till a point where you can understand it fairly well. Okay. Steps for generating a decision. First is that you start with the root node. So root node means all the data is present out there, right, in the decision tree. Decide on some kind of a splitting criteria and some kind of a stopping criteria, right? So one, though splitting, I think you understand that, okay, on what basis the tree should be split. What about the stopping part? See, you stop growing the tree till a part where your objective is satisfied. If you see that people, I mean, in the good parks, you will find that these people who are doing the gardening or maintaining those trees, they will also cut the tree, prune the tree, so that the tree comes in a shape, it looks good, it follows a particular pattern, right? So decide on those kind of a stopping criterion also. Will I let the tree grow fully, or should we have some kind of a stopping criterion out there? So once you have decided on this, then what you do is you start splitting the decision. So what happens is this: the root node split into two or more different subsets, right? So the branches keep on coming from the root nodes, right? So the trunk doesn't come, unfortunately. In a decision tree machine learning, we don't have a trunk, but we directly have the root, the branches coming out of the root, right? And then what happens is that these branches keep on dividing and further dividing till the part they are getting into something called the leaves. Once the branch gives rise to these leaves, the decision tree can't be split further. That is where you stop the decision tree and try to look into the tree and analyze that whether it's a good tree or not that you have created, right? So once you reach to that particular part where the tree can't be further subdivided, that is where you said that you have stopped the tree, and that is the part where you can start generating the business rules from this decision. Okay? That is how you do. Okay. So this is a flow chart for the decision tree. One is that whether you would like to use it for classification or use it for doing some kind of a prediction of some numerical values, right? So one is that if you want to just classify, and the response variable has only two categories, just two categories are there. So use a very standard classification. So in the initial days, the ID3 algorithms which were there, that uses this kind of a methodology. Now, if this particular tree is having multiple categories, not two, more than that, right? So which means that it's not a binary tree. There are more branches which will come out of the tree. Then use this C4.5 implementation which is there, which is much more versatile, as I said, than the normal ID3 algorithm. Second is, if you are having some kind of a prediction from the tree and the response variable is continuous, right? So if there is some kind of a linear relationship between the predictor and the response, linear relationship, so use standard regression, very standard regression. You have already learned regression. A standard implementation of regression is what we chew out there. If not, if the relationship is not linear, you can use this C4.5 implementation. We are going to talk about this C4.5 in the card tree, which we are going to do is actually nothing but a extension of this C4.5. That is what we are going to discuss in the session. Right? Quickly. So let me come here. A very simple classification tree, right? Is a person fit or not? Very simple classification tree. So first is we will look at the age part. Age is less than 30, right? Yes. If the age is less than 30, generally I would like to assume that the person is fit. They have a high metabolism rate, but still you'd like to see that whether the person eats a lot of junk food or not. So pizza is basically a metaphor for junk food. If it is yes, probably this person is unfit. Probably. Otherwise, no, this person is fit. If the age is more than 30, right, that is when your metabolism comes down. Then probably you're asking that whether this person is exercising in the morning or not. Yes, fit, no, unfit. Very simple if-else rules that you can form from decision. And like previously, someone might question the professor, why did we take the age criteria first? We could have taken the eats a lot of pizza part, or maybe the exercise in the morning part first. Because if someone is exercising, irrespective of the age, maybe they are fit, right? See, at the end of the day, as I said, what we try to do is we try to come to a decision with the least number of steps. If we follow this particular pattern, age and then the exercise and the eating part, maybe that will lead me to a fully grown tree in a shorter number of steps compared to the case where we would have started the other way around. Also, in terms of the variable importance, so whenever we are looking into the data is showing that this age part is probably more important in determining if the person is fit or not compared to all the other ones. Right? Let's see an example. So here is a data set which you're having. And now in this data set, what you have are 14 instances where the outlook for the weather is given, whether it's going to be sunny, overcast, or rainy. How's the temperature going to be? Hot, mild, cool, those kind of things. Humidity, the wind, and based on which whether you are going out to play or not. That is what we are going to find out. So this one, this play decision, is my target variable. So my first question to the batch is that, what do you think? Is this going to be a classification kind of tree or a regression kind of tree? What is your take on this? A classification tree or a regression tree? I've got 2 answered, 3 answered, right? All are saying classification. Wonderful. Yes. My decision is a category which is there. Right? The category is yes or no. It is a classification tree. By the way, sometimes what you'll find is that this decision comes in the form of a binary variable, 0, 1. In that case also, it's a classification tree. Sometimes the categories themselves, they are encoded in some numbers. 5 categories, 1, 2, 3, 4, 5. So though it looks like numbers, but still it will be a classification tree. So when you are looking into output variable in this particular case, it is very much on your face that it's some categories. So we are going to take a classification tree. Sometimes even if the output decision is some numbers which is there, have a look at the number. Is this number really a continuous number, or these numbers, they are standing for some particular categories? The numbers are standing for some categories. In case of a binary 0, 1 case, use a classification tree. Otherwise, it's a regression tree, right? Okay, so this is the data which is there. Now, my question to you is that, how am I going to determine that on which variable to split? I can split on outlook, I can split on temperature, humidity, wind, right? That is where the problem starts creeping in. Had you been a domain expert, like the case where we are talking about this salary part, that whether you're going to change your job or not, maybe you could have easily answered this. But because you are not a domain expert in this weather part, so probably since the data is there, we can take the help of the data, getting all along with how the decision could be made. Okay, some question is there. So Pinkesh is saying outlook is the main problem. Okay, so again, why outlook is the main problem? Why outlook is the main problem? Anyone? Right. So when you are saying it's a main problem, see, one is on the face, it might seem that okay, this particular variable is the culprit or main problem which is there. But don't just get bogged on with your past understanding of this. If you're a domain expert, well and good. Right? If you're not a domain expert, maybe you have to do some analysis. Right? So more important parameter, whether the outlook is more important parameter or not, we don't know at this particular point. We have to find out, and then we have to see that which one is more important compared to the other. Right? So some quick statistics I'll show. One is total 14 cases are there. If you've seen the data, total 14 cases are there 9 cases are saying play tennis. 5 cases are saying don't play tennis. Right? Now, if I have to look into just this data and take an overall decision, right? These 14 cases are actually a proxy for our entire big data that we'll be having. If I look the majority cases, so 9 of the 14, they are saying go out and play. 5 of 14, they are saying that don't play. So if I have to take a decision based on just the output variable, I'll say that the majority is saying go out and play tennis, irrespective of any other decision which is there. I don't even know that what variables are there. I see majority is saying that go out and play tennis. I'll say that's the decision. Now the fact is that you have been supplied with some variables based on which you can take the decision, right? So how we can use that to create our decision, right? So let's say this. So one way we can do the splitting is based on the temperature, right? Temperature is greater than equal to mild, go out and play tennis. If the temperature is lesser than the mild, don't play tennis, right? Now this blue and the red are the cases where you have actually arrived to a decision. Some kind of a decision you have already actually arrived, right? So if your temperature is giving you a good enough decision, very well, we'll take that. Otherwise, you are seeing that even after this temperature part, I still have some kind of uncertainty. This gray part is where this uncertainty is. So what you decide to do is that you decide to split it further. This time I'm deciding to split on the humidity part. Right? If the humidity is normal, then go and play tennis. Not normal, don't go out and play tennis. So now, once again, back to the question that, okay, why temperature first, then humidity, why not humidity first, then temperature, all those things, right? That is what we are going to figure out. How we are going to do it is by the process of divide and conquer. Right? Divide and conquer. I'm sure that everyone knows this terminology, divide and conquer. What we do is that some particular, see, what you do in a divide and conquer methodology, right? The Britishers, they have used for long a divide and conquer methodology on us. Even the political parties this day, they use that. So they will try to find out some loophole, some particular point, right? Some weakness, attacking which you can be divided and split it, right? So we are going to try and attack those points where if we are able to find out that these are the areas where we can target, the tree will be, the decision can further be split. That is what the divide and conquer part will do. And how we are going to do the divide and conquer is, one is first, you have the root node, right? I'm going to subject this root node to some particular kind of test, right? And see that against which particular test the division is much more smooth compared to the other cases. So which means that if I have to maybe find out decisions based on people who are probably believers versus non-believers, on which particular point should I play some kind of a religion card? Should I play some kind of other cards like gender, poverty? What is the card which I'll play so that I can split this particular bank which is there, right? So what we do is first, once we do find out some of these points, we try to test it on the root node. On which particular point are you getting the maximum split? So do this particular thing recursively until when you don't have any further instances left to reach that particular branch. How? Let's see. So the Kite algorithm, in the first place, it's the chi-square automatic interaction detector algorithm. What you need to do with the Kite algorithm? Very simple. Each and every variable you look into and find out that how these variables are playing a role in splitting the decision tree. Let me show you. This is the formula for this chi-square if you have looked into the optional content. So there's one which is called the observed value, where one which is called the expected value, which is out there. right? One is which you are observing, one is which you are expecting, right? Degrees of freedom is also there. Okay, I'm not going to details into that. But what you do is, once you find out the chi-square value, there's a something called a chi-square table which is there. What the table will give you is the probability of observing this particular value when the null hypothesis is true, or in the particular sense. Okay, if I have to say it in layman's term, right? If this probability value is very small, then probably the variable which I'm taking is important for taking the decision. Otherwise, it is not important in taking the decision. Right? Okay. So Pinkesh is asking what is x in the chi-square formula. So again, so this it's not x, it's actually chi. So chi-square, that's what is written. So chi-square is what we are going to find out from this particular formula, and C stands for the degrees of freedom, right? How much freedom this the data is having based on the variables which has been given to us, right? Again, if this has not been covered in details in your STS, will not dwell deep into it. It will eat a lot of time, but just for the sake of knowledge, you should know the chi-square tree, right? Okay. Now, how we are going to proceed with the chi-square tree? First, let me look into my data. Let's look at the variable outlook. If I look at the variable outlook, there are 9 cases for play and 5 cases for don't play. And this variable outlook can be split further into sunny, overcast, and rain. When it is sunny, 2 cases are saying play, 3 cases are saying don't play. When it's overcast, 4 cases are saying play, none of the cases are saying don't play. So see, already if you split by the outlook and you happen to come to a node which is overcast, right? If the overcast is there, already the decision is very clear, go out and play, right? And the third one, rain, 3 cases it's saying play, 2 cases it's saying don't play, right? So you might ask that, okay, how it is like this? Again, that is coming from the data. So this is how the data looks like, but at the end of the day, 9 cases of saying play and 5 cases don't play, and this is how the distribution of the data is. If I go and look into the temperature variable, this is how it looks like, right? Hot, mild, and cool. Take the case of this hot, right? If the temperature is hot, see this particular part. Very difficult for me to take a decision. 2 cases are saying play, 2 cases are saying don't play. Difficult for me to take a decision. If the temperature, by the way, is mild, okay? So here I am seeing a majority is saying go out and play, and there are some cases also which are saying don't play, right? So 66% is saying play, and then 33% is saying don't play. If I see this part, cool, 75% is saying play, and 1 is saying don't play, right? This is how the data is distributed across these ones. And then finally, we also have the wind, right? In the wind case, you see with the wind is strong, very difficult for me to take a decision. 3 cases are saying yes, 3 cases are saying no, very difficult, right? For the case wind is weak, yes, in this particular case, I see that almost 75% is saying play and 25 is saying don't play. So this is how the variable is interacting in the final decision, which is play versus don't play. I'll have to figure out that which particular variable is more important. Again, so by the application of this, okay, so humidity was also there. So the humidity case, you see, difficult to take a decision out here. Here, decision is probably much more easier. Where 6 of the 7 cases, which is almost, I think, 85% chance of playing, and 15% chance is not playing when the humidity is normal. Right? We are not a domain expert, but what we can do is we can use the statistics which is there and pass it on to this some method or the other. Here, if we do use a guide, right? What I'll quickly show is this is what the guide gives us: outlook, temperature, wind, and humidity. These are the different values of the variable which are there. Now, on what condition you do the splitting? Typically, the case where the probability value is the smallest, on that particular factor, you do the splitting. Here we see that humidity has the lowest probability value. That is what will be used for splitting out here, right? How we get this p values? Yeah, Puna is asking. Pinkesh also had some question. See, once you calculate the chi-square value, there is something called a chi-square table, right? So you go to the chi-square table, and against the chi-square value, you can find out the p values which are there, right? So you won't have to calculate this p value. Already there is a standard statistical test which is there. Like you have this normal test, normal table. So like that, you also have a chi-square table from which you can get this p values out of it, right? Okay, so this is the kite part, but again, and I'm not going to ask you kite in the exams, but again, just for your knowledge, I have included this. I think this kite was not there in your teaching content, but I think you should know it since you're studying this decision. Come to the part, divide and conquer part once again, right? Let's use something like this ID3, which is there, where you can do a binary kind of split. So first, select a feature, split the data, ask more question, continue till there are no further splitting possible, right? First, I split this. If this thing is homogeneous, no further splitting necessary. If it's not homogeneous, that is when I split it further, right? This one also I split it further till the point we are getting to a point where my decision on the nodes, they are homogeneous, right? How to do that, right? So let's look into the techniques now, right? So how we are going to do the split? In the initial, if you remember, I told you that first there is some kind of a splitting criteria that we are going to use, and there is also something called a stopping criteria that we are going to use. Let's talk about the splitting criteria, right? So this is the case. If you see on the left hand side, my data is totally pure. Why I'm saying data is totally pure? There's no impurity, right? If you're talking of water, the left hand part is where my water is completely pure. So I don't need to split this further, right? This is a good enough for me. See on the right hand side, the green parts are the water, but also there are dissolved particles, the red and the green ones, right? So if you have to make a pure water out of this, what you need to do is you need to filter out this blues and the reds, right? That's what we'll probably try to do, right? So what we are going to do is we are going to measure this impurity value. Right? So again, in terms of your probability, you can say that impurity is the complement of purity, right? So higher the impurity, right? We have to the more disturbed the data is, lower the impurity, better the data is, right? Okay, so let's look at some ways in which we can split the data. See, here is a data point which I'm having, where there are 12 data points in the root node, 12 data points. 8 of it is saying yes, and 4 is saying no, right? And then I'm doing a split based on this temperature. If I do the split based on temperature, what happens is that 2 of them says yes right now, and 2 of them says no right now, right? If you remember the data that we had, this is how it looks like. And on this particular part, we have 6 cases which says yeah, go out and play tennis, 2 cases which says no, don't go and play tennis, right? Now, how much is the impurity? We need to check, and in the process, whether we were able to reduce the impurity or not. If in the last session, if you remember, we had used this classification error equation, we are going to use it here also. So classification error at the root node, my impurity is 1 minus maximum of the probability of the two classes which are there. Or this is 1 minus maximum of 4 by 12, comma 8 by 12. So this is 1 minus 8 by 12. So 4 by 12 or 0.33. That is the impurity, amount of impurity which I have at the root node. Right? Pinkish has already given the answer. Thank you so much for that. Now, once I have done that splitting, if I see on the left hand part, if I apply the same paradigm, I'll find my impurity value is 0.5. While on the right hand side, if I do the same thing, I'll find my, anyone can give me the impurity value on the right hand part? Impurity on the right hand part, 6 cases of yes and 2 cases of no. Okay, only one person is giving the answer. What happened to the others? Very simple. 1 minus maximum of 6 by 8. 8 data points are there. 4 data points are here. And 2 by 8, which is 1 minus 6 by 8, or this is 2 by 8, or 1 by 4, 0.25. So what you see is that at the root node, my impurity was 0.33. When I've splitted it, one particular branch is showing an impurity of 0.5, while the other is showing an impurity of 0.25. Right? So here, I have been able to, on the right hand side, I have been able to decrease the impurity. But on the left hand side, the impurity is not decreased, it has increased. Right? Now, is this a good split? Right? This will be a good split only when the combined effect of the impurity, the combined impurity has decreased. Now, in the root node, if you remember, there were 12 data points. Once I split it, 4 data points have come on the left hand side, 8 have come on the right hand side. So the contribution of the impurity from the left hand side with regard to the previous one is 4 multiplied by 0.5, and the one which is there, I'm sorry, not 4, 4 by 12. And on the right hand side, we have 8 by 12 multiplied by 0.25. Right? So 4 by 12 is 1 by 3. So 0.5 by 3. So let me quickly make the calculation. So 0.5 into 4 is 2 plus 0.8 into 0.25. I think once again, this is 2. So this is 4 by 12. 1 by 3 only, right? So overall, if you see that whatever impurity I had at the root node, the parent node which was there, by splitting by this temperature, I have not been able to reduce the impurity much. Right? The combined impurity, though you can say that the right branch is more useful as Pinkesh said, but again the combined impurity is still lesser, is still the same as what we had earlier. So probably temperature was not a very good variable for splitting the decision tree. Right? Anyone who did not understand, please raise your hand. I can repeat this particular part, because again, if you understand this, the rest of the part will become very easy. Anyone who has not understood, so it's very simple. One is we find out the root node and see the amount of impurity which is there at the root node. Now, what is this impurity? Right? If you see the impurity, impurity is the amount of disturbance which is there. So this one, pure, no impurity, right? But again, once I start making some of it red, some particles are there in the water, that is when it starts become impure, right? So in the purest form, impurity is 0. But once you add some particles to it, that is when the impurity starts rising. Right? The case where you have all the particles in equal proportion is when the tree is, when the your data is maximum impure. All the targets are in equal proportion, right? Okay, so coming back again to follow from this analogy, let me rub this slide again. Once you understand this, I'm sure that the rest of the part will be pretty easy. So first what we do is, see, if in this particular case, all the 12 were saying yes, a completely pure node, I don't have any decision to take. All the 12 are saying, yes, go out and play tennis. Or all the 12 are saying, no. Completely pure. No further decision to take. Right? But the very fact that there is some kind of a dilemma in the decision, that is where the impurity comes in. And how we measure the impurity is by this matrix which we call. So classification error is one of the matrices. Right? Then we have the Genie index, entropy. Those are also some of the evolved matrices which are out there for doing the splitting. Now, first, when I calculate the impurity via, so this is the classification error equation, which just gives me the amount of impurity which is there. Just to give an example, if all the 12 were saying yes, then my C would have been 1 minus maximum of 12 by 12. Right? And nothing else, right? So it will be 1 minus 1 or 0. So 0 impurity means completely pure. But the fact that there are some kind of a problems, so 8 by 12 and 4 by 12, that is the proportion, and this is where we get 0.33 as the impurity value out here. Fine, so I have the impurity at the root node. What I need to do is I need to select some variable or some filtering method which can help me separate this impurity from my data. Right? If I split by this temperature, what I see is that temperature and also on this mild part, 4 data point, 4 of the 12 have come here and 8 of the 12 have come here. In this 4 of the 12 data point which has come, if I consider the impurity again, unfortunately the impurity is 0.5. Here impurity is 0.25, right? By the same formula which we did. So now if I am trying to measure the combined impurity, I repeat, if I'm trying to measure the combined impurity is 4 by 12 of the impurity coming from this particular node, 8 by 12 of the impurity coming from this particular node. So 8 by 12 into 0.25 plus 4 by 12 into 0.5. That's what we did. And that's what gave us the impure value. Right? Okay, could you explain 1 minus maximum to 0.33? Okay. See, 1 minus maximum of 8 by 12 and 4 by 12. Simple this particular ratio. So this is 1 minus, between this 8 by 12 and 4 by 12, between these two, I think this 8 by 12 is the one which is more. So 1 minus 8 by 12, this is equal to 4 by 12 or 1 by 3, this is equal to 0.3. I hope, Stevens, you got the idea now how this is coming. Okay, but the same way we are getting the other ones. So when we said that on the left hand side we are getting 50%, so the how we got was 1 minus maximum of, so 4 data points are there, 2 are saying yes, 2 are saying no, 2 by 4, 2 by 4, which is 1 minus 2 by 4, which is 2 by 4, half 50%. That's how we got 50% on the left hand side and then 25% on the right hand side. Not to worry, I have already shared the slides with the upgrade team, with the NM team. All the calculations are there. Right? So this is the change in the impurity which I got. So after doing the split on temperature, change in the impurity is 0. Not a very good split which I have done. Right? Okay. See, one way to do infer is that this particular variable is not good for splitting. Otherwise, see, one problem is there is that this classification error, that's actually not a very good metric for splitting. I'll show you why. But there are more evolved metric, like one is this Genie impurity, which is there, right? So Genie impurity is simply computed by summing up the probability of occurrence and non-occurrence of the different classes in the data. So if in the data I'm talking about, let me show you the example with Genie impurity. Same data, right? 8 yes, 4 no, 2 yes, 2 no, and 6 yes, 2 no. So 4 by 12 of the data coming here, 8 by 12 of the data coming out here. If I consider the Genie impurity at the root node, right? So this is how it will be calculated. So if I just do the calculation, so for the first class, it is 8 by 12 into the complement of that. So 1 minus 8 by 12. Plus for the second class, which is no, 4 by 12 into 1 minus 4 by 12. Or this is 8 by 12 into 4 by 12 plus 4 by 12 into 8 by 12. So like that I'm getting, right? Typically, if you have to use a simpler formula, this boils down to this 1 minus the probability square of the corresponding classes. So here in the root node, 1 minus 8 by 12 whole square plus 4 by 12 whole square. So this is giving you out this value of 0.444, which is outlined out here, right? So can anyone help me out with the Genie index of this particular node? Maybe people who are facing the difficulty. I think Stevens was having some difficulty, and then I think there was someone, Kamlesh or someone, who also had a difficulty, right? So can you help me out with the impurity value based on the Genie index for the left hand part quickly? Stephen, I'll be very happy if you can give the answer. Okay. Yeah, impurity value. How to find out the impurity value for the left hand side of the node? Quickly. It's already 8, right? Quickly. Pinkish is saying 0.9375. Okay. Okay. Anyone got the same answer? 0.9375 Pinkish is saying. I'll also have to do the calculation, but see on the left hand part, if I see, so 1 minus probability of these two classes. So the yes class is 2 by 4 square plus the no class is again 2 by 4 square, right? So if I do that, right, are you getting 0.9375? I don't know. Yeah, I think it is 0.5. I think it is 0.5. I think it is 0.5. Right? Okay, let's quickly proceed. So yeah, if we do the splitting on the Genie impurity on the left hand side, 0.50, and on the right hand side, you'll find that it is 0.375. Once again, if I look into the combined impurity, so this 0.54 by 12 is being contributed by this 0.5, and 8 by 12 is being contributed by this particular right hand part. So if we take that into account, right, this is the overall change in the Genie impurity. A very small value, 0.02, but yeah, still some changes have occurred. Right? So Stevens, yeah, thanks for the answer. Yeah, the answer is correct from your end. So some bit of impurity we have been able to reduce. That's what we see with Genie impurity. Right? The other metric which is there, which is more being used. So this Genie impurity and this entropy, they are the widely used metric. Right? And see, the root of all this impurity measures are there in the different literature. So for example, if you see the classification error part, the root of the classification error impurity part is then probability theory. If you see the Gini index part, what we did right now, the root or the basis lies in the econometrics part or economics. Entropy, anyone who has studied physics in the undergrad, entropy, anyone knows entropy? Have you heard of it? Class 11, 12 physics, if you remember, for people who have studied science, right? So entropy, yeah, Puna is saying that she never remembers. Yeah, Puna, I'll just probably put you degree of randomness. Okay, Puna, I'll just turn off your this thing. You can probably speak to the class. It's good if you some people speak. Just a moment. No, for some reason I'm not able to give you the control. I'm so sorry, but yeah. So again, if you remember the Stevens is saying volatility. Yes, yes. So what happens is this entropy comes from physics, Brownian motion. Yeah, thermal energy. Yes. So the more you heat a particular metal, what happens is as the temperature increases, the friction or the randomness within the molecules it increases, and the entropy is higher, right? And when you cool it down, it becomes lower, right? So that the same analogy they have used out here. So we are seeing the amount of restlessness in the data. If all the data were of the same type, it's a pretty cool system. If there is a lot of disturbance in the data, different types of data are there, so that is when they are fighting against each other, right? So that is when the entropy becomes higher. And how you calculate the entropy, there is a nice formula for entropy. Minus of pi into log of pi. That is the entropy formula, right? So pi into log pi. Now how this is interpreted? So pi is the proportion of the data which is there, right? So here, if you see 8 belonging to class A, 4 belonging to class B, 12 data points are there. So 8 by 12 log of 8 by 12 plus 4 by 12 log of 4 by 12. This is how the entropy looks like, right? So if you had something else, you can probably put that also into the piece. Some other variables were there. Now, there's a minus sign in front of it, and in some books you'll find that it is interpreted or it's written in a different way. So in some book you'll find that entropy is written as pi into log of 1 by pi. This is also something which is written, and there you will not find the minus sign. There will be a plus sign only. Anyone knows why this minus sign is there in front of it? Anyone? Any idea? Simply mathematical this thing. Simple mathematical this thing. Yeah, Pinkish, you have a point? Yeah, Pinkish. Unfortunately, I'm not able to put you on your mic on. Yeah. So Pinkish, if you're having a question, yeah. Okay. Log of less than 1 is negative. Wonderful. Yes, that's a reason. That's why in some of the books you'll find it is written as pi into log of 1 by pi. But again, for the consistency, I like this one better, easier to remove. Remember, pi into log pi, just put a minus sign in front of it once you do the calculation. Great, great, good. So you can use the entropy equation also. See, once again, this entropy can also give you this impurity value which is there. Don't mix and match these impurity values, right? If you're using entropy, use entropy throughout the problem. If you're using Gini index, use Gini index throughout the problem. If you're using classification error, use classification error throughout the problem. Don't mix and match, right? Okay, quickly. So what I'll do is, so Pinkish has a question, which method is best out of the three? I'll come to that particular point. Not right now, give me some time. Okay, so if I calculate the Gini index, the entropy values. See, there's another question that entropy 0 means more homogeneous. Yes. So see, if it's the case where there were all the 12 were of the same type, then the proportion Pi will become 1 and log of Pi will become log of 1. Log of 1, you all know, is equal to 0, right? So in that particular case, impurity value is 0, completely pure, right? More the impurity value, right? More is the amount of randomness in the data, right? So quickly, if I can find out the entropy on the left hand side, you understand that entropy will be 2 by 4 log of 2 by 4 plus 2 by 4 log of 2 by 4 whole with a negative sign. For the right hand part, entropy will be 6 by 8 log of 6 by 8 plus 2 by 8 log of 2 by 8. Once you find out the entropy at the root, left hand side, right hand side, the method is once again the same. You find out that how much reduction in entropy has happened. So in the root node, this is the entropy, 0.9183. On the left hand side, entropy is 1. Right? Both the decisions are with equal proportion, maximum entropy 1. On the right hand side, entropy is 0.8113. If I see the reduction in impurity, change in the entropy, it is 0.441 is the change in entropy which I get if I split based on this temperature variable. Right? So now that you have understood the concept of this impurity value, and also once that you have understood this change of impurity, how we can use to solve a problem. Let's see that, right? Okay, I'll come to the question which I think Pinkesh had mentioned. Okay, Pinkesh is asking on the left hand side how it is 1, and then also which method is the best of the 3. Okay, fine. So how it is coming as 1 in the left hand side? Very easy. Minus 2 by 4 log of 2 by 4 minus 2 by 4 log of 2 by 4, right? So 2 by 4 is half. Here also 2 by 4 is also half. Log of 2 to the power minus 1 minus half log of 2 to the power minus 1, right? So that is where we are getting. So log of, see this log is to the base 2. If you see the equation, so log 2 is 1, right? So half plus half, right? That is how it is coming as a value of 1, right? Hope you got that. Okay, no, not bested. Generally we use for a binary tree, we use a log to the base 2. So if you have more classes, if there are 3 classes, 4 classes, 5 classes, then you use the log appropriately. So Joginder and then I think Pinkesh also asked that which method is the best, which metric is the best, right? And that's a popular question for the interviews, right? Which metric is the best? If I plot the AUC curve, right? AUC curve shows this particular revelation. The one which is there in brown, this is the measurement of the classification error. Only 50% of the cases can be handled using classification error, right? If I say Gini index, you see the Gini index comes with a bulge. So obviously this Gini index performs better than the classification error part. But again, if you look into the entropy, the one which is in the blue, this also has almost the similar shape as that of Gini index, but the bulge is even more. So the AUC for the entropy is the maximum which we get out here. That's why amongst these 3 techniques, entropy is by far this technique. Right? Most of the cases, what you'll find is that entropy and this Gini index, these are the ones which are used. If I remember in the Python implementation, by default, I think they are using Gini index as the metric for splitting. Classification error, as you're seeing that it's probably not the best. Only 50% of the cases it is able to account for. Now, why 50% of the cases? If someone is asking, simple. This is the area, total area which is available. So this particular part is a triangle with the same base covers 50% of the area which is there, right? Half of base into altitude, right? Okay, I hope I answered that question. But again, this is a very popular question in interviews, that which metric is the best one. If you're able to draw this particular curve and explain, you get full brownie point for that, right? Okay, so the information gain is what we generally use for this entropy. So what we do is that entropy of the parent node minus the entropy of the child node and in the particular proportion. So here also, if you remember, we had found out the entropy at the root, which was this minus 8 by 12 log 8 by 12 plus 4 by 12 log 4 by 12 entropy at the root, and here entropy at the child was 8 by 12 into 2 by 4 log 2 by 4 plus 2 by 4 log 2 by 4. That is one part, and the other part had 4 data points, right? I'm sorry, this one had 4 data points, so 4 by 12, and the other had that 8 data points, which was 8 by 12 into 6 by 8 log 6 by 8 plus 2 by 8 log 2 by 8, right? Information gain, same concept which is there, right? So quickly, I'll do the ID3 algorithm. Okay, this is the problem which is there. We'll solve this problem and we'll go for a break after solving this problem, right? Okay, this is my problem. My features are gender, whether someone owns a car or not, what's the travel cost, and what's the income level. And the output of the decision is what kind of a transportation mode this particular person is going to take. I need to find out a decision based on the features which is their gender, car ownership, travel cost, income level, as to what kind of a transportation mode will someone follow. To do that, first, what I need to do is, by the way, can anyone tell me the distribution of the classes in my target variable? The distribution of the classes in my target variable? The distribution of the classes in my target variable? Can anyone give me the answer? Distribution of the target variable? Distribution of the target variable, can anyone give me? How the target variable is distributed? Anyone? One answer from someone, I'll be happy. I'll obviously solve it for you, but yeah. Bernoulli, no. I'm asking a very simple thing. Distribution of the target variable, if you see, there are 10 data points. 10 data points, 3 classes, 4 for bus, 3 for car, and 3 for train. This is how it is distributed, very simple. So if I look into the proportions, 4 by 10 of them, they are going for bus, 3 by 10 going for car, and 3 by 10 going for train. Bus, car, train. Right? Okay. Now, how I can use this? First and foremost, what I need to do is find out the impurity at the root node. Right? So now you are going to help me. So these 3 impurity values which are there, one is CE, one is Gini index, one is entropy. CE, can you give me the value quickly? CE at the root node. Pinkish is saying 0.6. I think it's the correct answer. So 1 minus maximum of 0.4, 0.3, 0.3. Of these three values, maximum is 0.4. So 1 minus 0.4 is equal to 0.6. Great. GI, if I need to take, this will be 1 minus 4 by 10 squared plus 3 by 10 squared plus 3 by 10 squared. Entropy, if I have to take, it will be 4 by 10 log of 4 by 10 plus 3 by 10 log of 3 by 10 plus 3 by 10 log of 3 by 10. Right? Okay. So again, you just know how it is done. I'm sure that you are not going to do it by your hand. But again, having the idea maybe helps you better in the process. Okay, so probability bus, car, train, these are the values. Classification error 0.6 we have got. Entropy we have got as 1.571. And Gini index we have got as 0.66. Entropy 1.571. How come? How come entropy 1.571? Anyone? How come we got entropy more than 1? Anyone? Entropy more than 1. Why we got? I mentioned this just maybe around 10 minutes back. Anyone remembers? See, typically this log 2, when we are taking, it's basically devised for a binary kind of tree. When you are having two decisions, yes, no, 0, 1, those kind of things. Here we have 3 decisions, right? That's why when you are using this log to the base 2, the value is exceeding more, right? If you use log to the base 3 out here, you'll find that the value comes down to be less than equal to 1. But again, nevertheless, whatever you're using, please use that consistently, right? Right? So yeah, base 2 is generally fixed. Base 2 is generally fixed. In fact, most of the packages also, they would have implemented this base 2 part. But again, that doesn't make any dent in your interpretations, right? We are going to interpret it. Let's see. Yeah. Okay. So this is what we have at the root node, right? So once we have this, let's split based on this travel cost. So travel cost cheap, you'll find that there are 4 instances of bus, 1 instance of train. Travel cost expensive, all the 3 case car. Travel cost standard, all the 2 cases train. So point to be noted is that for travel cost expensive and travel cost standard, I've already reached a homogeneity. I've already reached the right decision, right? The data has become completely pure when my travel cost is expensive and when the travel cost is standard. Only when the travel cost is cheap, I still see that my output is not yet homogeneous. So 4 instances of bus, 1 instance of train is there. If I compute the impurity based on entropy, it is 0.722, Gini index is 0.320, and classification error, it is 0.20. Right? So at the root node, if I go back, root node, my classification error was 0.6, right? Entropy was 1.571 and Gini index was 0.66. And here, after splitting by this travel cost, cheap travel cost, right? Expensive and standard has already become homogeneous. Cheap, there is some issues. We need to work with that. Okay. So what we are going to do is this information gain. If we use impurity in the parent table minus sum of the probability and impute at the child table, that's what we are going to use. This is what we get. Reduction in the impurity value when I use entropy is 1.210. In Gini index, it is 0.50. In classification error, it is 0.50. Right? When I split based on travel cost. My question to the class is that right now, can I conclude that I can split based on this travel cost? Yes, no, maybe. Can I split based on the travel cost? Will that be a good decision? What do you think? Will that be a good decision if I split based on this travel cost? Okay, so Amritangshu is saying no. Good. Why? Pinkesh is saying no. Why? Why? Yes, no is very subjective. Why? It's not right. I think Jugindra has given the answer. We have done only for the travel cost part. We have not seen how the other features or the other variables they are behaving. We need to find the gain info for the other variables as well. But great, all of you are on the same page. Okay, so this was based on the travel cost. Let's see all the others, right? So on the left hand side, this is via the gender. Here, this is via the car ownership. This is via the income level. This is what I have got. Now, what we need to do is we need to do a comparison. So I'll show you the comparison table. Okay, so again, I'm not going to details of the calculation. By this time, I think you have understood how entropy is calculated, Genie index is calculated, classification error is calculated. Right? If I go into the, this is my result. If I split by gender, entropy, change in entropy is 0.125. Car ownership, change in entropy is 0.534. Travel cost 1.210. Income level 0.695. Genie index 0.060, 0.207, 0.5, 0.293. Classification error, if I do 0.1, 0.2, 0.5, 0.3. My question to the class now is which one to take? Which one to take? Which one to take? Right. I've got one answer from Pinkesh, but yeah. Amritangshu said entropy. See, entropy is just the measure. Entropy is just the metric which I've used. You can use any metric. So let's say that I only had this entropy, nothing else. Let me cross this one out. Which one to take now? Amritanshu is saying car ownership. Priyanka is saying gender. Okay. Okay. See, if you remember, I am going to take that particular feature or variable which gives me the maximum reduction in impurity. Maximum reduction. Yeah, Mali, I think Anu has given the right answer. So travel cost is the one which has given us the maximum reduction in impurity compared to the others. If I split by the travel cost, the impurity is reduced to the maximum possible extent. So that's why we need to take the travel cost as the splitting point. Right? Okay. So if you see, so here all the three metrics are there, right? So you won't have to calculate all the three. Either stick to classification error or stick to Genie index or stick to entropy. Right? So if I do this anyone, if I take the Genie index, you see this one is where the maximum reduction of impurity has happened. So that's the one which I'm going to take. Right? So if you see the reduction in order, this is where the first, second, third, and fourth. This is the order in which they have appeared. Right? Okay. Okay, Pinkesh is asking initial results, so we can see the amount of reduction. Yes, we can do. Why not? So this was the initial classification error 0.6, entropy 1.571, and Gini index is 0.66. Right? This was the root node, and this was what we got for the this thing after the first split. So just to quickly give you the classification error part. So classification error at the root node was 0.6. So 0.6 was that the root node minus impurity. Here I have 1, 2, 3, 4, 5 data points. So 5 by 10 into 0.2 plus 3 by 10 into 0 plus 3 by 10 into 0. So this is 5 by 10 into 0.2 or half into 0.2, which is 0.1. So 0.6 minus 0.1, this is equal to 0.5. That's how we got it, right? All the others I'm not showing, but this is how it has been calculated, right? So I hope you understood, Pinkesh and all the other people, right? Okay. Quickly, yes. Okay. So I am done with splitting via this travel cost. Now the other variables which are remaining are gender, car ownership, and this income level, right? So already this has become homogeneous, right? After the split, I don't need to do any further splits of this, already homogeneous. This is where I'm concerned. This is where I'm concerned, right? So you see all the travel cost cheap, transportation mode, 4 are bus, 1 are train, right? If I move ahead, this is the particular node which I need to work with. The other node, already homogeneous, either car or train, I don't need to work with it. This particular node, I have 3 other attributes which are there: gender, ownership, and income level. If I do further splitting, right? Once again, if I look into the impurity part, this is the impurity right now at this particular node. So this is the root node right now. These are the impurity values. If I do the splitting based on gender, based on car ownership, and based on income level, these are the reduction in impurity. My question to the class is, which one am I going to take right now? If you have understood properly, which one I'm going to take right now? Which is the one variable which I'm going to take right now? Sumit is saying gender. Anu is saying gender. Priyanka is saying gender. Yes. Everyone correct, right? The answer is gender, right? So gender, if you see that has the maximum value by entropy, maximum value via Gini index. Unfortunately, for the classification error, it's not able to give you any further result. So yeah, classification error, not the best way of doing the split. So yeah, good. So we'll split based on the gender part, right? So gender, this is how we are. So gender female and gender male. So gender male, already homogeneous. Transportation mode is bus. Gender female, still there is some doubts, right? Because one is saying transportation mode bus, another is saying train, right? So we probably need to split it further, right? And for splitting further, I have this car ownership, income level. Actually, both these variables, only 2 data points are there. So both these variables are equally distributed. So take any one of it. So this is how my tree looks like right now. Travel cost expensive, car. Travel cost standard, train. Travel cost cheap, go to gender. Gender male, always taking bus. Gender female, further need to split. After I have done the splitting based on probably the either the car ownership or the income level, right? So car ownership, no car, bus, 1 car, train. That is how the decision tree is created from this, right? This is how iteratively you create a decision tree. And if you see the child nodes, it is completely homogeneous. I don't have any bit of ambiguity in the child nodes or in the decision, which means my decision tree is completely built, right? So this is how decision tree works, irrespective of any method that you use irrespective of any metric that you use. To sum up, we take all the data in the root node. We see the amount of impurity which is there. So impurity you can measure by anything, right? So impurity you can take the entropy, the classification error, Gini index, anyone you can take. But again, I'll advise you to use either Gini index or entropy because those are much foolproof compared to the classification error. And check that after you split by a particular feature, how much amount of impurity you have been able to reduce. The one feature where splitting gives the maximum reduction, that is the feature that you take, and then iteratively you continue till the time all the nodes becomes homogeneous. Right? So Puna has a question: travel cost entropy has log 2 or log 3. The base is on the number of final response variable, number of results of the decision. Okay, see again, Puna and everyone. So whenever you are using a particular metric, you need to stick to that particular metric. That's the reason I have consistently used the log 2, right? Don't change it to log 3, log 10, something like that. If you want to use log 10, yeah, please go and use log 10 consistently. If you want to use log 2, please go and use log 2 consistently. It's not that, okay, you are changing the log basis in between. Whatever you start off with, you maintain it till the end of the problem. So if you're using entropy, please use entropy with the log. So generally take log 2 or log 10. Okay, don't make it so complicated. So use that. If you're using Gini index, please go and use Gini index. If you're using this particular classification error, please go and use classification error. ऐसा नहीं है कि you start off with the classification error and then you're not able to split further and then you switch to Gini index like that. No, don't. Right? Stick to whatever piece you have started off with. Right? Okay. So as you can understand why decision tree is so popular, one is no domain knowledge required. Right? Even we didn't have any idea about the domain knowledge, but still we could create right decision based on some simple mathematical premises. Right? Very easy to understand, less data cleaning required. Right? Data type is not a constraint, can handle categorical as well as continuous. And sometimes the classification is based on probability alone. Right? Most of the time, that's what we are doing. Okay, Amritanshu is asking, can we create decision tree in Excel? No, I don't think you can create a decision tree in Excel. That is probably not possible. What you can do is you can do the calculations in Excel. So whatever calculation that we have done out here, yeah, maybe you can use Excel to do the calculation, but no, you can't use it in Excel. You can probably have to use R, Python, or some other evolved tool to do that. Okay, so I think we are at 8:43. Can we quickly take a break and come back exactly at 8:50? Should we take a break? Yes, no, maybe? Sure. So let's take a break. Let's come back exactly at 8:50. Please don't be late, right? I'll start off with the hands-on part, right? I'll just show you the hands-on section. If the file you have received, well and good. If you have not received, okay, I'll send them a reminder. But again, whatever concept that we discussed, we will show it in the hands-on part. Right? Okay, quick break. We'll come back exactly at 8:50. 8:49 is when I'll restart. 8:50 is when we'll get loading. Right? So I'm just pausing the recording. Please remind me to start it once again. Thank you, everyone. Let's break. Okay, let's slowly come back, right? 7:50 exactly. And this file, the data set I've already shared. If you have not got that, I'm sure that will be sent across this particular file and the data set. So here the data set is the popular Titanic data, which I think many of you have already seen. Right? The objective is to find out that if this particular piece, this particular decision which is there, if you see the data set, I'll show you the data set soon. This is that if someone was survived or someone did not survive based on several variables which are there, right? That is what we are going to do. Okay. So I think there's some question. Let me just check. Yeah, Shubhendu is asking, reconfirm Python coding will not be a part of the TE. No, I'm not going to ask for Python coding in the TE, but by the way, your projects will come up sometimes I think in the next term where it will be entirely on Python, right? So yeah, and next term I think some part of the evaluation also will contain Python. So yeah, you better make yourself prepared in this particular part, right? And if you're trying to carve out your career in the data science zone, they will expect you know either of R or Python, if not both. Okay. So first, what I'm doing is I'm importing this libraries which are there. So pandas is for reading the data frame, numpy for doing numerical calculation, matplotlib for plotting, right? So let me just first import this libraries. Done. First thing to do, I'm reading this particular data file, which is the Titanic data clean. It has already been shared with you, right? And my data file, the contents of that is in a data frame, which is called data. If I look into the shape of the data, right, it contains 891 rows and 25 columns. That's what the data contains, 891 rows and 25 columns. If I look into the first few rows of the data, this is what the first few rows look like. Data.head, data frame.head will give you the first few rows. And these are the variables that we have. One is survived as the variable. By the way, the survived variable is the one, which is our target variable. 0 means did not survive. 1 means survived. Age is there. The fare they have given, that is there. The passenger class. So either they were in passenger class 1, 2, or 3. A binary variable has been used for that. The gender, whether they were female or male. Number of siblings which were there. Number of childs which were there. And their port of embarkment. Right? These are the variables which are there. See, all these variables, whatever you see, are the features. And this survived column is the target that is there. First thing generally that we do for any data science problem is we check for missing values. So we are just checking that whether there are some null values in some of the columns. As I've told you that this is a clean data file, so no null values are there. In that way, it is a good, right? No null values are there. Wonderful. So let me just describe the data. Once you describe the data, what it does is that in terms of statistics, it gives the 5-number summary along with the mean and the standard deviation, right? So this is how the data is looking like. See, one thing you should understand is that, see, this survived column, it's just a binary variable, right? And still you see that it is giving some kind of a mean, standard deviation, minimum, 25%, 50%, 75% maximum. Doesn't have any sense. Age, yeah, I can understand that age is a continuous variable. You can do a statistics, sorry, on that. Fair, yes, you can do that, right? But all the others, passenger class, number of siblings, number of childs, embarked or not, right? These are just binary variables. No point in doing any statistics on that. So if I look into the data types, how it has interpreted the data. So survived is interpreted as an integer. Age is interpreted at some floating point. Fair, floating. All the other classes are as integers. So what I can do is, one, I can change them to Boolean, right? All the other variables I can change to Boolean, right? That's one way of doing it, right? All the variables if you see, I can change it to Boolean, right? By default, or it's better because you are using them as categories, change them to some kind of a categorical variable. See, all the other data points except the age and the fair has been changed to category. Now, if I do a describe, you find that survived, age, and fair, only this three has been taken as numerical variables, right? If I do a info once again, survived is still as an integer. All the others, they have been changed to some kind of a category, category 0 and 1. So now let me put this data for why we do not change survive. We are going to do that. Inkesh, hold on for some time. Now what I'm going to do is I'm going to create the feature and the target variable I'm going to extract out of this. How I'm going to do this is data.survived, right? This is the particular column I'm interested in. I'm replacing 0 with deceased, replacing 1 with survived, and changing the type as category. Right? So at the end, I'm doing it. I could have done it earlier also, but yeah, this is where I'm just doing it. And that is my y variable or my target variable. My x variable is the features variable, right? Where all the other variables except survived is there on the x variable. I'm done, right? Now what I need to do is, as you know, I have to split this data for training and validation. Right? I'm using the train test split. So from sklearn model selection, I'm importing this train test split, which is there. And from this, I'm actually splitting the data. Train size, if you see 75%, 0.75. So I'm saying that 75% of the data is being used for training and 25 for validation. Done, right? So my x train, x valid, it contains the features for training and validation. Y train, y valid contains the features for the data for doing the prediction. If I do a count of this target y train, so there are 412 cases of deceased and 256 cases of survived. Right? If I look into the percentage, what you can do is in this value counts, just give normalize equal to true. 61% deceased, 38% survived. I have one question to the class. This stratify equal to y. Does anyone knows what is this stratify? Anyone knows what is this stratify? Anyone knows? Anyone knows what is this stratify? Good. I think Puna has given the answer. What it does is based on the y variable, the distribution of the target variable, it splits the data proportionally. Otherwise, what will happen is that maybe you end up with some training data set where all one particular feature has come in, the other feature has not just come in, right? That can be a problem. So the stratify, what it will do is it will split the data proportionally. Good answer. Pinkesh has some question in row 61. Yeah, what's the question, Pinkesh? I didn't follow your question. And if you can just refrain from using this all caps, I'll be happy, right? Yeah. What is this question? Row number 61, X, Y drop. So here from the data, survived column is the one which is my target. So I don't require the survive column in my features. So I've already taken the survive column in my target. So that's why from the original data frame, I am just dropping the survive column and all the data is coming in my features, which is the X part. Right? Okay. So in the Y variable, only the survive column is there from the data. And in the X variable, all the data except the survive column is there. Okay. So Stevens is asking that didn't get the stratify. How would it split? And stratify is false. How would it split? Right? Okay. So Stevens, what will happen is, let's say, right, let me just pick out let me open up a whiteboard. Quickly, I'll not spend time on this because tomorrow I'm going to spend a lot of time on this particular one. Let's say I have 100 data points, right? And 90 is of class A, 10 is of class B, right? This is how my data looks like. And let's say that I am using 70% data for training and 30% for validation. So as you understand, 70% means 70 data points will come from the for training and 30 data points will come for the validation. This part I'm good. Now it might also so happen that all in this 70, all 70 are A, and in this 30, all 30 are only 20 are A and 10 are B. That can happen. So now if I'm training using this, what will happen is my tree or whatever machine learning model, it will get trained on this part of the data, which is having only class A. So for the class A, it will work fine. For class B, it will totally fail. That's the problem. So when we use this stratification, what it will do is it will split the data in the proportion in which they occurs in the target variable, which means that 63 will be A and 7 will be B in the 70 data. And here in this 30%, we will have, I think, 30% is validation, which means on this 30 data points, I'll have about 27 A and 3 B, right? That is how it will come out, right? So hope you got it, right? The stratification part. Again, we are going to do it in details in tomorrow, not to worry. Let me share my this thing with you again. Okay. Okay. So yeah, 61% is this thing in the training data part. If you see, 61% is deceased and 38% is survived. If you see my validation data, so here also it's coming in the same proportion, right? In the validation data also, you'll find that 61% is deceased and 38% is this survived, similar to what we have for the training data, right? So that, I mean, the data doesn't get trained on something and expects something else, right? This is how my data looks like. 668 rows for training, right? And 24 features. And this is how my validation data looks like. 223 rows for validation and 24 features, right? Now I'm all set. What I'll do is I'll use the sklearn.tree. From that, I'll use the decision tree classifier. This is the classification problem, right? I'm creating an instance of the decision tree out here, right? In the DT underscore. Let me do one thing. Let me just increase the font a bit. It will be easier for you to follow. Yeah. So first, I'm creating an instance of the decision tree. Next, what I'm doing is I am just fitting the training data on the decision tree model, right? And now, if I would like to see how my tree looks like, so there is a text representation of the tree. So I just do the text representation. This is how it looks like, right? This is how my decision tree looks like, how the survived, non-survived case are coming. So internally, this is how the tree has been created. But again, I think you can understand that very difficult for us to figure out from this data how it is looking like, right? So maybe we are going to use some more methods which can make our life easier. Otherwise, It's very difficult. It's easier for the machine to understand, not very easy for us to take the this thing. It's saying feature 0, feature 1, right? Very difficult, right? So let me come down. Let me come down. Okay. So if I check how well it has performed, this is the scoring. So this is, by the way, giving me the accuracy of the training data. Right? Accuracy of the training data is what I'm getting out here. If I look into the accuracy of the validation, this is what I'm getting. So while on the training, it is 98.8% accuracy is there. On the validation data, I find 75.3% is the accuracy. Right. So now, if I just use the confusion matrix accuracy score and classification report, I'll just build a function. This is how the prediction looks like, by the way. So prediction survive, disease, like this. This is how the prediction is doing on the validation data. Right? If I have to convert that to a probability value, I can just do the prediction, and then correspondingly from that, I'm putting a threshold on this and saying that when the Y value is less than 70%, put it as 0, otherwise put it as 1. So this is for just for segregating out the probability classes, right? Not really very much required, because again your model will automatically do it. This is by the hand, I'm just showing you. And this is how the result is looking like. Yeah, this is my confusion matrix. Right? This is my confusion matrix. So 114 cases of true positive, 54 cases of true negative is what I have in the data. Right? So you can see the metric out here. Right? So here it says that the precision is 70%, the recall is 80.83%, right? F1 score is 0.83, and 157 data points are for class deceased. And for the survive case, if I look into once again, the precision is 70%, the recall is 63%, the F1 score is 0.6, and the number of data points that we have is 86. So if you remember, 223 data points were there for my the validation part. This is where it is coming out from. Right? So I can see my model is doing a pretty good job on the disease part. On the survive part, yeah, if you see, the recall is less. The F1 score is also pretty less. That's what we see from the data, right? Okay, let's move ahead. Let me do a plot of this tree, right? There is a tree.plot thing which is there, which will plot the decision tree. Still running, takes a little time to get generated. It's already churning out the results. Let it come down. Okay. Still is not yet completed. What it will happen is, yeah, see, this is the tree that it has created. What is the problem with this particular tree? Right? Is this tree fine, good for consumption? What's the problem with this tree? What is the problem with this particular tree? Anyone? Are we good with this tree? If you get a tree like this, show it to your organization, will they be happy? Somebody comes is saying, no. Why? Why? See, it is very, very deep. It is very, very deep. Now, to get some kind of a meaningful meaning out of this, too much complex. Yes, that's a problem. All of you are right on target. That's a problem. Right? Even if I do a plotting of this tree. Just this particular tree, I'll do the plotting. Right. So it is just putting it out. Just several time to output. Not to worry, the output will come. Yeah. So as someone rightly said that, okay, the tree is too complex, too lengthy. It probably needs a bit of pruning. Even after using these colors and everything, I'm not yet able to figure out how the decisions are happening in the tree. To counter this, what we are going to do is, let's not build this tree so deep. Let's probably build smaller trees. Right? So what I'm saying out here is that let me have this depth from 1 to 15. So I'll build a simple tree with one depth, and maximum I'll have the depth till 15. But again, see, one problem that you have is that if you build a shallow tree, maybe the model will not be able to do a good prediction. So that is what we want to check right now. That is my model good when I'm doing a shallow tree, or if the performance is very bad. So let me just quickly do this. Okay. So what we have done is that we have built a decision tree with varying depth. So depth I've taken in the range of 1 to 15. Right? This is what I have taken, the depth of the tree. And we have fitted model. We have looked into the accuracy of the training data and validation data. This is how the accuracy looks like. Depth is 1, training accuracy is 80%, validation accuracy is 73%. Depth 2, training accuracy once again 80%, validation is 73%. Right? Depth 4, 84%, 77%. Depth 5, 84%, 77%. Like this, you can get, right? So I'll just put a diagram for you that how it looks like. This is how it looks like, right? So the one on the blue is for the training performance, and one on the orange is for the validation data performance. So what we can see is for the blue one, for the training performance, as and when you have increased the depth of the tree, the performance has kept on increasing. But we are more concerned with how this particular data will do on my validation data. So if you see the validation data, initially it started off very low. It picked up out here, and then it remained steady for some time. It picked up at this 0.8, and then after that it has steadily come down. So if I see the best performance of the decision tree based on the validation data, the depth at which it happened is probably 8. So if I can probably grow a tree up to the 0.8, I think I should be good. Also, something I would like to show it here. Tomorrow we'll discuss in more details about this particular part. Whenever you try to build a model, try to have simpler model. See out here, if I see the decision tree at a depth of 3, right? This particular point at a depth of 3, if I have the, let me just use the annotation. If I look the decision tree at this particular point, vis-a-vis this particular point, on the training data, yes, significant improvement has happened. But on the validation data, if you see, there's a very minute increase in accuracy which has happened. Sometimes it makes sense for you to create simpler trees so that again, your decision, your interpretation, those are simple compared to having a very complicated model, right? So if I do that, right? So these are some of the pieces that I can do. One is leaf nodes. How many leaf nodes I can have? how many different minimum number of samples I can have in the left, and minimum number of samples for splitting. These are also some of the parameters which I can put. Right? So Stevens is asking, would the graph values change if we read on all the cells of the notebook again with the same values? I did not get the question, Stevens. If you rerun the cells with the notebook with the same values, yeah, it will remain the same. It will remain the same. Right? Only problem happens is for the training split, right? Different times, different split happens for the training. But there, if you also put in some kind of a random number, it will also be the same every time you run it, right? That's why you'll find that whenever we did the splitting, initially, I think I did not mention that, you'll find that there is a variable which actually controls. Yeah. We have given a random variable out here, right? So this will control the size of the tree out there, right? Sorry, not the size of the trees. I'm sorry. The splitting part it will take care of, right? So okay. So now let me put a decision tree, a simpler decision tree with a depth of 4, maximum number of leaf nodes as 25 is what I'll do. Once again, putting this model to training, getting a score of this model, 84% is the score on the training data. 77% is the score on the validation data. Now, if I plot this tree, see this time I have a much simpler tree. The depth was 4, so 1, 2, 3, 4. Till that depth only the tree has been built, right? If I can probably increase the font a little more. Let me see. Yeah, I can do that. Yeah. No, I think it's too much. It's 5%. Keep it at 300%. Yeah. Problem is, I'm not able to navigate to that particular part. What to do? Not able to navigate. Just put out this tree. Let it run. It will be visible. Okay. No, I'm not able to. Just a moment. Just a moment. Just a moment. Yeah. Now let me expand it. Let me give it a 200%. Some issues is happening. I'm so sorry. Whenever I'm doing the zooming part, I'm not sure. This particular part is getting yeah. Okay. Yeah. I think this is good. Okay. I don't think you're still able to see this thing. Maybe I don't know, a little visible, probably a little better than what we had previously, but here the values of the decision tree are there. The values of the decision, left hand side, the folder icon. Okay, let me just try it out. Yeah, thanks so much. Yeah, now I think it is visible, right? Now I think it's visible. So you see that it is giving you the split for the tree, right? The Genie index, it has found out 0.473. 668 samples were there, right? 412 were for the class which is deceased, and 256 is for the class which is survived. It says class equal to deceased. Any reason why it writes class equal to deceased? Any reason why you think the class it writes as deceased? Anyone? Because see, that is the maximum class, this thing, the maximal class which is there. More of the classes are of the deceased type in the root node, right? So what in the root node we are doing is we are splitting based on the gender male which is there, right? So if I split on the gender male, right? I'm sorry. So it's saying that sex male is less than equal to 0.5, right? So basically it is, and if you remember the male values, it is 0 and 1. Female values are also 0 and 1. So less than 0.5 means the male it will take as 0, which means that it will probably take the female values. So now if I see the female values, if you see this one right now has 247 samples, 61, 186, this writes class equal to survived. So what it means is that when we split based on the gender, a majority of the females, they had survived, right? You see on the right hand side, this is where the males have come in, right? 351, total number of samples is 421, of which 351 male, of which 351 is deceased and 70 is survived. So majority of the males, they did not survive. They did not survive. Let's come back here. On the left hand side, you'll find that if we split this further based on the passenger class, right? So passenger class 3 is what we are taking. Passenger class 3 is basically the third class kind of passenger. So passenger class 3 is less than equal to 0.5, which means passenger class 3 is 0, right? So it is not considering the passenger class 3. Majority of the cases who survived were not from the third class data which is there, right? Also, for the people where they were on the third class, depending on the fare which they have given, if you see the fare, right? If the fare is on the higher side, right? More of them they survived. Fare they paid was lower, they did not survive. So like that, it has created the decision tree, right? Okay. Questions quickly. Some questions if you have before we move back to our piece. We'll continue with this one. How we are fine-tuning the model, we are going to discuss tomorrow. But yeah, questions? No? Let me move back to my slides again then. We'll just discuss some of these points. Okay. So we come to the part which is the overfitting and the underfitting. As some of you rightly said, that decision becomes too complex, right? So that is the part where sometimes taking the decision itself becomes very complex, or again, it's not fit for taking a decision. It's an overfitting case. The underfitting is when the algorithm can't capture the underlying trend of the data. Let's say that I have not split the data at all. So no model has been created. So when you are going to do a prediction based on this data, it's going to just predict the maximal classes in underfitting cases, right? So avoiding the overfitting part, how we can avoid the overfitting? One part to avoid the overfitting is the pruning part, as some of you were saying. Stop the growth of the tree before it reaches to the point where again it becomes super specialized, right? So that is one way of doing it. But again, your question might be that, Professor, how do you know at what point to prune? Right? So one of the methods which people uses is that first you let the tree grow fully, and then from the fully grown tree, you prune it to the performance level at which you are looking at. And also another thing that you can do, which we are going to talk about in the ensemble learning class, is rather than tree, you can use a forest. Right? By the way, what's a forest? What's a forest? What's a forest? Anyone? What's a forest? Purna is saying boosting. No. I mean, simple English terms. Yeah. Stevens is saying collection of trees. Yes. Very simply, what is a forest is nothing but a collection of trees. So what you can also do to avoid overfitting is that you have a forest of small trees. And we will use, I mean, there are different methodology in which you can build this small trees, which is there, right? So a collection of those trees will lead us to a forest. So that's also another way in which the overfitting part, which is there, which can be stopped, right? But again, coming back, what we can do to tune the decision tree to stop this overfitting, to make sure that the tree does better. One is the maximum depth part. What should be the depth of decision tree? Should we stop at level 1, level 2, level 3? What point we should stop the decision tree? There's also something called the minimum sample split. Right? Sometimes, as you understand, that tree becomes overfit. If you remember the problem that we solved, in the problem we were growing the tree fully. The problem were transport modes like train, bus, car, it was there. But we were left with one points in the leaf nodes at the end. So sometimes what you can also say that minimum sample split, right? Minimum this number of samples should be there before I'll attempt a splitting. If there are less than this number of samples, so let's say I'm saying that my minimum number of samples for splitting is, let's say, 30. If in a particular node there are less than 30 data points which are there, I am not going to split it further. Minimum sample split. Another is a minimum sample leaf, right? So that is, so minimum sample split and minimum sample leaf are very closely related. Here I am saying that I am not going to split a tree, a particular node, if it is having a lesser than a threshold number of data points. And minimum sample leaf is saying that this is the minimum number of data points which is going to be there in my leaf node. If there are lesser than this number of data points in my leaf nodes, I'll probably not go to this particular leaf. I'll probably grow my leaf at a different level. Also, you can also work with the split criterion. By default, as you have seen, the Genie index is being used in Python, but you can also use the entropy. You can specify the entropy as the splitting condition. Right? Okay, so here is some example for that. Right? So let's say that I have given a minimum sample split of 70. Right? So if there are 70 nodes out here, it will not allow further splitting because there are, if you split the tree further, there will be less than 70 nodes which are there. Right? See here, the tree in the tree, 70 data point has come out here, and 30 data point has come out here. If you put a minimum sample leaf of 30, right, it will not allow further splitting because again I've said that the minimum number of samples in a leaf should be 30. Now obviously whenever you are putting a decision tree which is there, right? So what you can do is in the very beginning you can say that okay, this is the minimum sample split, these are the minimum sample leaves, all those things you can specify at the very beginning, right? And when you specify those things, the tree will be built accordingly. For example, here this tree has a depth of, this is the first depth, second depth. If I say that the maximum depth is 2, and let's say that you had not given this or you have not given this, but you have only specified that the maximum depth is 2. After this particular point, the tree will not be split further. Maybe this particular point, if you had removed this minimum sample leaf, maybe this will split further. Maybe 10 data point and 20 data point will come like this. But beyond this, there will be no further splitting. Right? So these are some of the points that you can make so that you get a tree which is probably of optimal size. Now, whether a depth of 30 is optimal, right? 10 is optimal, 5 is optimal. I have already shown you that how we are putting out the optimality curve out there, right? So what you can do is you can iteratively you can use one or the other variables and see at what point you get the optimal values. There are other methods also which are called the grid validation methods, which will give you the optimal points across the entire space. I think I had discussed grid validation in the last class, but again, in tomorrow's session in the model selection part, we are going to talk more about all these things. Right? Okay. So yeah, maximum depth, right? You can specify. Also the maximum number of terminal nodes that you have, that also you can specify. And the maximum samples for node split, minimum samples for leaves. These are some of the points that you can use so that you can prune the tree. You can have a tree which is not fully grown, and you can control the performance of the tree. Right? Okay, so we will stop here. We will continue with the just one part of the decision tree is remaining, which is the regression decision tree. We'll take it up in tomorrow's class. But again, if you have some questions right now, I think it's a good time to ask your questions. Let me solve whatever doubts or clarifications you require. Whatever doubts you require, please put it in the Q&A part, in the question part. Let me answer whatever doubts that you're having. Right? Just to summarize, what we did was we took up this decision tree and we said that in the root node have all the data, find out the impurity at the root node, and then once you take some features, find out that how much of the impurity has been reduced, and based on that you can create different features you can test, and whichever feature gives you the maximum reduction in the impurity, that feature you take to split the tree. Right? And then what happens is that once you have created the tree, fully grown the tree, the problem which is there is that the decision tree sometimes might overfeed, it might become too complicated, and so that you have to prune the decision tree in some way. So what you can do is you can tune by maybe not allowing the tree to go up till a particular beyond a particular depth, have some minimum number of leaf nodes which are there, have some minimum number of samples beyond which you're not going to do the splitting. Right? All these methods you can use to stop doing the decision tree further. Right? That is all in the nutshell that we have devised today. Today you have also done created a decision tree by your hand, and now I think you all know how you can use these impurity measures, how you can reduce the impurity values and all these things. Okay, so Pinkesh has a question. You have not received the PPT as it is to PPT. Okay, no, so maybe I have not named the PPT as it is to PPT, but yeah, it should have been sent to you. Okay, so Amritangshu has a question: application of forest in real life. So Amritangshu, I am not very sure that what you mean by application of forest in real life. Again, we'll take on the random forest part in our ensemble class. But again, just to give you an idea, what we do is that whenever we are keeping a forest, so then what we do is we create small decision trees, right? We probably build decision trees which goes up to maximum 1 or 2 depth. And like this, many decision trees we grow based on many data samples which are there. And then from this forest which is there, we find out that, okay, which particular feature is the one which has been more used in this particular forest. Those becomes my decision points in which I'll split the decision. Like in the first example where I asked you, okay, how you're going to find out that which is the most important variable. Is it salary? Is it the commute? Is it the perks? Most of you said salary, because again, that's the combined decision. All of you think in the same. So forest also works in the same way. So Amritangshu has again another question: can you use the forest for technique case? We can use the forest not only for technique, for any case. For any case, we can use the forest. Right? That's only another different model which is there. Right? This is just another model. Random forest is just another model for solving your classification or even the regression kind of problems which are there. Right? Okay, so yeah. Puna is asking, the rest of the slides will be covered in the next class. Yes. As I said, that the regression part we have not covered. We'll cover the regression part in tomorrow's class and we'll get ahead with the model selection part. Right? Okay. Any further questions anyone is having? I think it's a long day, right? Saturday evening, keeping your motivation. Yeah. Hats off to all of you. Fine. So I don't think there are any further questions are coming in, right? So let's break for today, right? Thanks for being in the class. Thanks for asking the questions. We'll again meet tomorrow and continue with the rest part of the discussion. Fine. Okay. Thank you, everyone. Have a nice day. Please make sure that you put your comments in the feedback so that the university can also work on these feedbacks and we can only give you a good learning going ahead. Fine. Thank you so much. Good night. All the best. Bye-bye.